Exponential distribution is defined in the following way. So the name is exponential exp, and it has one parameter, lambda. Lambda is called again a rate. Lambda is positive. And we will say that x is a exponentially distributed random variable with parameter lambda. And we will write x is exponential with parameter lambda if its PDF is given by this formula. So PDF is equal to 0 if x is negative, and PDF is equal to lambda times e to the minus lambda x if x is non-negative, x is positive or 0. So in this case, let me draw the PDF graph. So we will have this kind of graph for PDF. So 0 up to 0.0, and when x is 0 we will have lambda, so it is starting from lambda and it is decreasing and it is tending to 0 at plus infinity. So I will have this shape of graph. So this means that our random variable x cannot take negative values. It is taking positive values only. And easy to check just by integration that this f is a legitimate PDF. So the integral over minus infinity to plus infinity over the real line of this function is 1. So this is a small exercise. You can prove that the integral of this is 1 over the real line. And another exercise is to prove that the CDF of our exponential lambda random variable x is given by this f of x, which is 1 minus e to the minus lambda x if x is non-negative and 0 if x is negative. So to calculate that f of x, you need to calculate the area under the graph of PDF up to the point x. So if this is the graph of PDF, so the PDF graph was something like this. This was tending to 0. Then if x is here, to calculate the value f of x, you need to calculate the area left to that x under the graph. So you need to in fact calculate this area. This area will be the value of f of x. And in this case, I cannot use geometric ideas. I cannot calculate this geometrically, this area. I just need to integrate this function. The function graph is lambda times e to the minus lambda x. If you will integrate this, so this is, you will obtain the following. So let me write it here. So you will obtain the integral from 0 to x. In fact, we need to write from minus infinity to x, but because it is the PDF is 0 up to the point 0, we can just integrate from 0 to x for positive values of x. Lambda e to the minus lambda, I'm changing this to t, not to confuse with this x dt. And if you will integrate this, you will obtain 1 minus e to the minus lambda x. Exactly. I'm not doing the details. You can do that by yourself. So I will use a lot this formula. In fact, I will use both the PDF and the CDF for exponential random variable. Now the usage. This is very important random variable, and this is very much connected with the Poisson distribution, Poisson random variable. Later I will give some explanation. We will talk a lot about that. But first, about the usage of exponential distribution. We use exponential distribution to model the waiting time for some event to happen, the time until the next event will happen, or the time until the first time the event will happen. So let me give some examples, and later we will do some more. The waiting time x until the next order at some GG, at the GG taxi service or another taxi service during some time interval can be modeled as an exponential random variable. So x is exponential with lambda. We just need to calculate correctly that lambda. We can model that waiting time for the next order by exponential random variable. The time between clicks on a web page in some fixed time interval can be modeled as exponential random variable. Or the time between goals scored in a World Cup will be exponential, can be modeled as exponential. Time between two meteors greater than 1 meter in diameter will strike the Earth is again exponential, can be modeled as exponential. Or time between successive failures of machine or between discovery of new Bitcoin block, time a storekeeper must wait before the arrival of their next customer, or time between late arrivals to probability class when we were doing our classes at the classroom. So these are all models, cases when we can use the exponential distribution. Before going deep into this distribution and talking about different usages and connection with Poisson distribution, let's solve a problem. So x is exponential with a rate or with parameter 2.6. Give some interpretation for x. Well, x is waiting time between two events. So some events are happening and x is that waiting time between two events. Later we will understand what this 2.6 is meaning, how we can calculate this 2.6, that parameter. So x is some waiting time. Write down the PDF of x. Well, the formula for the PDF is the following. Say, it is 0 if x is negative, so waiting time cannot be negative, and it is lambda times e to the minus lambda x. So 2.6, our lambda is 2.6, this is lambda. 2.6 times e to the minus 2.6x if x is non-negative. So this is the PDF of our x, of our exponential 2.6 distribution. Now write down the CDF of x. So f of x is 1 minus e to the minus lambda x, 2.6 x. X is larger or equal than 0 and 0 otherwise if x is less than 0. So you can remember this formula or you can calculate by using the PDF, but I'm suggesting you to remember this formula because when dealing with exponential random variables it is much useful. To calculate probabilities usually we are using this CDF, not integrating the PDF. Well, you can do without this CDF, you can just integrate this. It is not so hard, but it is much easier to use this CDF for exponential case. Say for uniform case, it is much easier to work geometrically, of course. Okay, so let's move forward. Part D, probability that x is equal to 2.6. This is exactly 0. Because x is continuous random variable and taking a particular value for continuous random variable is with 0 probability. So now I want to calculate this. I have two ways to do that. Say, the first one is to integrate from minus infinity to 2 the PDF. And because our PDF is 0 for negative values, I'm just integrating from 0 to 2. That PDF was 2.6 e to the minus 2.6 x dx. So we can calculate this integral and obtain the value. But I want to show how to use the CDF value. So this is equal to CDF at the point 2. And this is equal to, well, because here we have positive number, I will use the first part of that definition of calculation formula for f. That was 1 minus e to the minus lambda times x. X is 2. 2.6 times 2. So this is that probability. Well, 2.6 times 2. Let me write 1 minus e to the minus 5.2. Okay. The next one, x is larger than minus 2. Well, x is always, x is exponential random variable. It is taking only non-negative values. So x is always larger than minus 2. So the probability is 1 just. Or by using formula, if you want to have with formula, I'm passing to complement 1 minus the probability that x is less or equal than less than minus 2, sorry. Although these probabilities are the same if I will write with equality sign. But this is equal to 1 minus the value of CDF at minus 2. But the value of CDF at minus 2 is 0. For negative values, CDF is 0. So this will give 1. Exactly. Okay. The probability that x is between 2 and 3.5. This is the value of CDF at 3.5 minus the value of CDF at 2. Well, of course, you can calculate by integrating the PDF from 2 to 3.5, but in this case, because we have a nice formula for CDF, I'm using this. So this is equal to 1 minus e to the minus 2.6 times 3.5 minus 1 minus e to the minus 2.6 times 2. And we will have this once cancelled. We will have just e to the minus 5.2 minus this value, e to the minus 2.6 times 3.5. Well, if you will calculate this number, you will obtain this probability. Now, the last part, the conditional probability that x is larger than 3, given that x is larger than 1. So let me calculate this. By definition of that conditional probability, I have this is a ratio of the following probabilities. Probability that x is larger than 3 and x is larger than 1 over the probability that x is larger than 1. Of course, if I'm calculating the probability that x is larger than 3 and x is larger than 1, then I have that intersection is just x is larger than 3. So I need to calculate the probability that x is larger than 3 over probability that x is larger than 1. Well, again, I can use integration from 3 to plus infinity of PDF, but I'm using, again, the CDF. So I'm passing to complements, probability 1 minus probability that x is less or equal than 3 over 1 minus probability that x is less or equal than 1. Now, 1 minus, this is the value of CDF at 3 over 1 minus CDF, 1 minus CDF at 1. This is equal, so I'm continuing here. This is equal to, recalling the values of that CDF. 1 minus, another 1 minus e to the minus 2.6 times 3 over 1 minus e to the minus 2.6 times 1. So we will have that once cancelled. Here I will have plus sign e to the minus 2.6 times 3 over e to the minus, I will have plus sign because I have minus here with plus sign, I will have with plus sign 2.6. So I will have e to the minus 3 times here, 1 times here, I will have 2 times 2.6, so 5.2. This is the value. In fact, it is easy to check that this is exactly equal to the probability that x is larger than 2. And we will talk about this later because this is very important property of exponential distribution. Okay, let's move forward. Another problem. So x is general exponential random variable with parameter lambda. We need to prove that this tail probability, the probability that x is larger than t, is equal to something. So easy to calculate. We have just calculated this kind of thing with a particular value of t with 3 or 1. So I'm passing to the complement. So 1 minus probability that x is less or equal than t. And I'm using the CDF. So this is the value of CDF at the point t. And I have the value of CDF of t for any t. Because t is non-negative, this will be 1 minus e to the minus lambda times t. And we will have that once cancelled, we will be left with e to the minus lambda times t. So this was what the problem was asking. This is what the problem is asking. Okay. So why I'm solving, why I'm giving this example, because this is giving an important notion. This function, as a function of t, is usually called survival function. So this probability that x will be larger than t is called survival or reliability function. So survival in actuarial insurance science, reliability in quality control science. So why is this important? Because if we will interpret x as a lifetime of something, then the condition that x is larger than t means that the lifetime is larger than t. So that person, say, will live larger than 60 years. So insurance companies need to calculate this kind of probabilities to decide what will be the premium for insurance premium. Okay, hope this was clear. So if x is exponential random variable, then the survival function will be given by this formula. And in that case, there is a name for that lambda. This is called hazard function or hazard rate. In fact, hazard rate. Yeah. Okay. Now, with R, generate in R 10 random numbers from exponential 2, and then do that for 1000 or maybe more random numbers, and plot the histogram of that data set to see how many numbers are in each of the intervals in bins. So let's go to R. The exponential distribution name is just exp. what I'm using. If I will write rexp, this will generate a random number. By default, the rate is 1. You can see that lambda is 1, but problem was asking to generate for 2. So I want to have just one number with rate for exponential distribution with rate 2. So I'm generating, it is giving 0.09. I'm generating again 0.3, 0.09 again. If I want to have 10 random numbers from exponential with parameter 2, I'm writing just 10. It is giving 10 numbers. Another 10, some numbers. So to have the picture of that, let's do the following. Let me just define x to be the following. Say I'm generating 10,000 numbers from exponential with parameter 2, and I'm doing, well, okay, thanks, and I'm doing histogram of that numbers, histogram x. Okay, so this is the picture what we have, if of course R will decide to show that to us. Okay, now I have the picture. So most of the numbers out of that 10,000, well, more than 6,000 are between 0 and 0.5. Some 2,000, say 300 around that numbers are between 0.5 and 1. And others are here. And well, around 1,000 are here, and others are here, etc. So no numbers at all, maybe that are larger than 4 in this case. Okay, I can change the histogram bin size, that width of rectangles. So I can do that. Breaks. I'm just giving the number of breaks. Let me give 20 breaks. Okay, so this kind of more precise calculation, say 1, 2, 3, 4, 5. This is from 0 to 0.2. So we have more than 3,000 numbers between in this vector x between 0 and 0.2. And we have around 2,000, say 400 values of x between 0.2 and 0.4, etc. So you can see that this histogram is repeating the shape, this decreasing shape of the PDF. By the way, let me draw the PDF and CDF graphs for exponential 2 here. So to plot the graphs, I am doing the following. So I am taking a running parameter. Say I want to draw the graph from 0, because I know that PDF and CDF are 0 for negative values. I want to draw from 0 to say 5 or 6. I'm taking a sequence of numbers from 0 to, let me write in this way, from is equal to 0, 2 is equal to say 5, by the step size is 0.01. So I have a lot of numbers. I'm dividing my interval 0 to 5 into with a mesh with size 0.1. Then I'm calculating, say y1 or y will be the value of our PDF at each point t, PDF of exponential distribution random variable with parameter 2. So PDF is by dexp calculated at the point t, and the rate is equal to 2. Now I can plot the graph, ty, line width is say 2, well, and type is equal to line. So I want to have, oh, sorry, this is not correct. This is correct. So this is the graph of PDF of that exponential 2 random variable. So it starts from lambda. Lambda is 2. At 0, the value is 2. It is decreasing to 0 at infinity. So we will have this kind of shape for the PDF. Okay. And now if I want to draw the graph of CDF, now I'm writing, say, the CDF from -1. Let me take from -1. I'm doing that again. I'm adding here z. Z is the value of CDF. So P exponential, CDF is by P. Calculated at every point of t, rate is again 2. Rate is again 2. And now I want to plot for that TZ, the points TZ. I'm running this and I have this kind of shape. As a legitimate CDF, it is tending to 0 at -infinity and it is tending to 1 at +infinity. So this increases very fast to 1. Okay, this is the CDF graph for exponential 2 random variable. Let's go back to our lectures. Okay, the next one, plot and compare PDFs of 2 different exponential distributions, say exponential 0.5 and exponential 2. Okay, I need to go back to our R. We have for exponential 2, so I'm erasing this. This is not important for us. T is running from, well, I can draw from 0. No need to draw from -1. So Y is PDF of exponential with rate 2. That's okay. Now, say Z is again PDF. Calculated at the same value as t, but rate is, say, 0.5. I'm plotting t z. Okay. I'm copying this. Control C, Control V, and I'm changing to y here. Well, this will not plot on the same graph, so I will have this kind of things. If I want to keep the previous one, I need to add, say, parameter new is equal to true. New is equal to true. Now, if I will run, I will have 2 graphs. I want to change the color of the second one, say, to understand which one is which one. The color is, say, red. Okay, now I'm running this. This will not be nice, okay, but let's see what is happening here. So I'm selecting and running. So what is wrong? Well, I have 0, 0.1, 0.5, then 0.2. So I have some mix of numbers here, not a correct scaling. So let me correct that. I need to add y lim. Well, x lim is 0 to 5 for both of them, so no need to change x lim. Y lim is from 0 to, well, the highest point. For this, the highest point will be 2. For this, the highest point will be 0.5. So I'm doing both from 0 to 2. Or let me write 2.1, a little bit larger. So I'm choosing this, Control C, and adding it here, Control V. Yeah, and now I'm running this both, Control Enter. Now I have the graph. Well, I have Y and Z here, but that's okay. Now red one was for Y. Y is with rate 2. Rate 2, it is starting from 2. So for the red one, what can I say for the red one? If I'm generating, if my random variable is with rate 2, with the PDF given by the red curve, then the probability that the values will be close to 0, say the values will be from 0 to 1, is very high because this area is very high. The probability that x will be, say, larger than 2 is very small because we have very small area under the curve. So if x is random variable with exponential random variable with parameter 2, then the probability that x will be, say, larger than 2 is very small. The values will be concentrated around 0. But what about the exponential random variable with parameter 0.5? Well, the probability that x will be larger than 2 is not so small. We need to calculate this parts area. Well, again, more elements will be between 0 and 1 than between 1 and 2, but there is a chance that the values will be between 2 and 3, 3 and 4, etc. So let me just check. Let me generate random numbers from exponential, say 20 numbers with rate which is equal to 0.5. So you can see that I have values larger than 2, I have value larger than 2, I have 4, 4, 4, 2 again. So I can have. But what if I am changing to 2 and running this? So you can see that, well, yeah, I have just one number larger than 2. And most of them are close to 0, 0 0.0, 0 1.5, 0 etc. So this is giving the density of probabilities, which intervals are more probable of having values of x and which are less probable. Okay, let's go back to our lecture. Now, about that interrelation, about the relation between Poisson and exponential, very important thing. Assume we are considering the occurrence of some rare events in some unit of time. A unit of time can be 10 minutes, or a unit of time can be 1 hour, or 1 day, 1 month, 1 year, etc. Some unit of time. We are fixing that. Poisson random variable is calculating the number of events in that time interval, and it is discrete. So Poisson is calculating number of events in interval. It is a discrete random variable. And exponential random variable is calculating the time between two successive events. So let me draw the timeline. Say this is time. We are fixing some time interval. This is our unit of time interval. And what we have some events happening here. Some events, say, this kind of events. So what is calculating Poisson? Poisson is calculating how many events were there. So say this is time interval from 10 a.m. to 11 a.m. And the event is car is passing through my window. So this is showing that 4 cars passed through my window, by my window, from 10 to 11 in one day. Maybe at some times, another day that will be 3 cars or 10 cars, etc. So Poisson is calculating how many events we have here in this time interval. And what is exponential random variable calculating? It is calculating time between 2 successive events, or time until the first event will happen. So this time or that time, time between the event, time between the first car passed and the second car passed, and time between second and third car, etc. So these are, and we have another car maybe here. So these times, waiting times, are exponentially distributed. So exponential random variable is calculating, is modeling this time passed from one event to the next event. So important thing is that exponential is continuous random variable. So Poisson is discrete random variable. It is calculating number of events, and exponential is calculating time between two events, successive events, or time until the first event will happen sometimes. Okay, and about rate parameter, I will go back to that interconnection between Poisson and exponential, but first about this rate parameter. So if we model exponential lambda by waiting time for something, so x is the waiting time for something to happen, and x is exponential with parameter lambda, then that rate parameter lambda is the inverse of the average waiting time. So what I mean by that, let me give example, and later we will talk about that again. So if the average time between two phone calls, that something is phone call, and the average time between two phone calls is 2.5 minutes in some call center, say. What I mean by average time between two phone calls, we are fixing times between two phone calls, consecutive successive phone calls, say 3 minutes, then 4 minutes, then 1 minute, then 0.1 minute, and then again 3 minutes, 5 minutes, and we are calculating the average time between two phone calls. And if we know that the average time is 2.5 minutes, then the waiting time between two successive phone calls in minutes, waiting time x in minutes, is modeled by exponential 1 over this average value, 1 over 2.5. This is a result from statistics. Later, when taking that statistics course, you will learn about that. But also we will consider the continuous version of this. What I mean by that, we will consider the notion of the mean value of a random variable. So this is a random variable. We will calculate the mean value or expected value of x. And we will show that for if x is exponential lambda random variable, then the mean value is 1 over lambda. So if x is our waiting time for something, then mean of x, or average waiting time, mean is average, x is our waiting time, so average waiting time will be 1 over lambda. So lambda is 1 over the average waiting time. That's why we are taking 1 over this average waiting time in the parameter. Okay, one example. So assume that the average duration of taxi order is 22 minutes. Let t be the duration of a taxi order. This is a random variable that depends on the order. And it can take 10 minutes to reach that destination. It can take 30 minutes, etc. Assume t can be modeled by exponential distribution. So write the distribution of t. So t is exponential. I'm saying that it is exponential. I'm giving that we can model by exponential. Now we need to write the parameter. Because the average duration is 22 minutes, then t is exponential with 1 over 22, and t is in minutes. The unit is minutes. This is what the previous slide was about. Okay, so t is exponential with parameter 1 over 22. What is the probability that the duration of the order will be larger than 30 minutes? Well, if I have this, then I have the CDF, I have PDF, I can calculate this probability. Let me just calculate. So the problem is asking, what is the probability that the duration t, duration was t is larger than 30 minutes. So I'm writing 1 minus p, t is less or equal than 30. And this is equal to, by the way, we have calculated this kind of thing for any exponential. If you remember, that was when I was talking about survival and reliability function. This is survival well, but every time I'm writing this with CDF, so CDF value at 30, and what is that CDF value? 1 minus e to the minus lambda, and lambda is 1 over 22 times t, so 30 in our case. So we will have these ones cancelled, and I can continue. Well, this is equal to, let me write it here, so e to the minus 30 over 22. So this is the value of this probability, the probability that the duration of the order will be larger than 30 minutes. Now, the C part, what is the probability that the duration of the order will be between 20 and 30 minutes? Calculate in two ways using the PDF and CDF. So we are asked to calculate the probability that t is between 20 and 30. Well, if I want to calculate by using PDF, I need to integrate that PDF from 20 to 30. The PDF in this interval is given by the following. So lambda was 1 over 22 times e to the minus lambda times t dt. Well, I can take this into the integral and calculate this integral, but I will not do this, calculate this by yourself. I will calculate the same thing, but using, I am preferring working with CDF in the case of exponential distribution. So I will do this with exponential, with CDF, sorry. This is f at 30 minus f at 20. And this is equal to 1 minus e to the minus lambda times this point minus 30 over 22 minus 1 minus e to the minus 20 over 22. And this will give, well, ones will be cancelled. This with plus sign, e to the minus 20 over 22 minus e to the minus 30 over 22. So this is the probability that the order duration will be between 20 and 30 minutes. Okay. Now going back to our rate parameter and exponential Poisson distributions. Now assume again that we are considering the occurrence of the some rare events in some unit of time. So rare events in some unit of time. Let y be the Poisson random variable showing the number of events in the time interval. So y is calculating how many the events are happening in that time interval, say in 1 hour. Y is Poisson with parameter lambda. And let x be the exponential random variable measuring the waiting time for that events, or time between that two successive events in the same units, in hours, say. And x is exponential, waiting time is modeling by exponential with some parameter lambda 1. I want to find relationship between lambda and lambda 1. Well, now the Poisson parameter lambda is counting. This is my timeline. So this is time. This is my interval. I am fixed here, unit of time. This is say 1 hours. And these are my events happened at some time instance. So Poisson parameter lambda is counting average number of events in that time interval. In 1 hour, this is one example of possible example. Say we have 3 events. Maybe in other, if we will consider another 1 hour, maybe we will have 2 events or 5 events, etc. So lambda is counting, lambda is showing the average number of events in that fixed interval. Okay, and continuing, what is doing exponential parameter lambda 1? It is the inverse of the average waiting time, as we have defined it. Inverse of the average waiting time. Now if in average in a unit time interval we have lambda events, say we have 3 events here, then the time between them in average will be 1/3, in fact. So then if in average lambda events happen in the unit time interval, then the average waiting time will be 1 over that lambda. If 3 events happen in 1 unit, then the average waiting time between events will be 1/3. So 1 over lambda. So because the average waiting time is 1 over lambda, and lambda 1 was 1 over the inverse of the average waiting time. Lambda 1 was the inverse of average waiting time, so we will have lambda 1 is the inverse of this. So we will have lambda 1 is lambda exactly. So what is the point here? What is the important thing? So if x and y are respectively, the waiting time and number of events in the same experiment in a unit time. So we are fixing unit time. Y is calculating how many events happened, and x is calculating the time passed from one event to another one. Then x is exponential with parameter lambda, and y is Poisson with the same parameter lambda, where lambda is the rate. It is the average number of events in that unit time, or the inverse of the average waiting time between that events. Let me just stress that we are talking about number of events and time between events for the same experiment. Well, we can have different experiments with Poisson and exponential with different parameters, of course. And another note, in general, if some events happen with a waiting time between them x, which is exponential lambda, so let me just give the timeline. Say I have timeline and I have event. The first event happening with some random value x, then the next is again with x, so I'm generating random times from x, another time until next event. This is timeline, this is time, another event, then passing some time, another, etc. Then if y is the number of events in the time interval of length t, say this is 0 time, this is t, and I'm calculating how many events are happening here if the average, if the waiting time for each event is given by this, then y is the number of events in interval of length t, is Poisson with lambda times t. Say if we are talking about unit time, for unit time we have Poisson lambda, exponential lambda. This is for unit time case, for the same unit time in a unit time. If waiting time is given by exponential lambda, and I want to find the distribution of number of events in, say, time interval, which is twice longer than that unit time, say this is in hours, say, and I want to have y is the number of events during 2 hours, then I need to write 2 times lambda, Poisson 2 times lambda here. Hope this is clear. You can think about that, you can ask your questions if necessary. Always ask your questions. I'm ready, I will be happy to answer them. Okay, so now using that relationship between Poisson and exponential, this is not so important, so you can safely skip this part, this explanation, but not the last part about memoryless property. Now what I want to do, I want to obtain the PDF of exponential lambda random variable y using the connection between Poisson and exponential. So I have distribution Poisson PMF. Having that Poisson distribution and having the connection between Poisson and exponential, I want to have the PDF of y. Let's see how I can do that. Let x be the random variable counting the number of events in the unit time. So y is exponential lambda and x is Poisson lambda. Y is showing the waiting time between events in a unit of time, in units of time, and x is the number of events in the unit of time. Y is modeling the waiting time, yeah, in the same time units. Let's find the CDF PDF for y just by using Poisson's PMF and CDF maybe, PMF is enough. Just by using the relation between Poisson and just by this connection, this interpretation, the connection between Poisson and exponential as number of events and time between events. Okay. Now assume one of the Poisson events just happened. One of the events just happened. Then y will show the time that will pass until the next event will happen, because y is calculating the waiting time until the next event. So I'm fixing one t, some t, non-negative, and considering the probability that y is larger than t. So I want to calculate what is the probability that I will wait more than t, say minutes or hours, that depends on the unit of time, say minutes. What is the probability that y will be larger than t minutes? So this is the same as the next event will take more than t time. Of course, the next event, y is calculating the time between two events. The next event will take more than t time. That is larger than t. And this is the same as no events in 0t. So next event will take more than t time. No event at 0t. What is 0? 0 is I'm starting counting from this Poisson event. One event happened and I'm counting, say, let me show that in a graph. So this is timeline again. This is when one of the events happened and I'm waiting for the next event. So this waiting time is y, and say t is something, well, some number, and y is larger, this is t, y is larger than t. So this means that this interval, this is 0 time, I'm starting counting from this point, 0 time, between 0 and t, no event happened. The next event was after time y. Okay, so let's see how to calculate. So I want to calculate what is the probability that there are no events in the interval 0t. Well, we remember how to do that by using Poisson distribution. But recall that Poisson lambda is for counting the number of events in unit of interval. Here I have 0t, so I need to change the rate for 0t. I need to have another parameter this for the interval 0t. If I will ask what is the probability that no event happened in 0, 1, well, we can use this x and calculate that, but here I have 0t. So let xt be the random variable showing the number of events in 0t. Since the average number of events is lambda in one time unit, 1 minute say, that is because x is Poisson with parameter lambda, then the average number of events in t time units will be in this interval will be lambda times t. So xt is Poisson with parameter lambda times t. So now I can continue calculating the probability that y will be larger than t is probability, we have obtained this in the previous slide, is the probability that no event happens in 0t, and no event happens in 0t means that this xt, the number of events in 0t, is 0. Now, because I have the distribution of xt, Poisson lambda t, this is equal to e to the minus lambda t. Exactly e to the minus lambda t. So probability that y is larger than t is e to the minus lambda t. So probability that y is less or equal than t is 1 minus this. And of course, the probability that y is less or equal than t is 0 because y is time between events, and if t is negative, the time between events cannot be negative. This probability is 0. So we have obtained the CDF of y. The CDF of y has this form, and this is exactly the CDF of exponential lambda random variable. So we have obtained the CDF form by just using Poisson random variables. And you can obtain the PDF from CDF just by calculating the derivative of this. Okay, now another problem about exponential distribution. Assume that phone calls at some taxi service are arriving at rate 2 calls in 5 minutes. So in average, we have 2 calls in 5 minutes. Let x be the number of calls in 10 minutes. So x is the number of calls in 10 minutes. And WT, waiting time, will be the waiting time in minutes between 2 successive calls. So x is counting the number of calls in 10-minute interval, and WT is calculating the time between 2 successive calls. So give appropriate models for x and WT. Well, x is the number of calls in 10 minutes, and we have solved this kind of problems, and we can model this x by using, we are modeling x by using Poisson distribution. So first about x. X is Poisson, and we need to find the parameter. So this is in 5 minutes, but we need to find in 10 minutes. So in 1 minute, we have in average 2/5 calls. So in 10 minutes, we will have 2/5 times 10, that is 4 calls. Well, this was easy in fact, because if we have 2 calls in average 2 calls in 5 minutes, so we will have in 10 minutes in average 4 calls. So 4 calls in average. X is calculating the number of phone calls during 10-minute interval in 10 minutes. So x is Poisson with 4. Okay, what about waiting time, WT? Will this be exponential 4? In fact, no, this will not be exponential 4, because if I will write here exponential 4, this will be calculated and not in minutes. Waiting time will be, say waiting time is, say I am obtaining 0.3. I cannot say waiting time is 0.3 minutes. I need to talk about 10 minutes. So waiting times, if I will write in this way, waiting time will be in 10 minutes. But I'm not preferring writing like this. So I want to have my waiting time in minutes. So to that end, I can calculate in 2 ways. Say calculate the average waiting time for a call. So what is the average waiting time for a call? Let's look here So we have 2 calls in 5 minutes. So because we have 2 calls in 5 minutes, the average time between calls is 5/2 minutes. This is the average waiting time. And here I need to write 1 over that average, 5/2. So I will have exponential 2/5. Hope this was clear. 1 over the average waiting time for a call, 2 calls in 5 minutes. So between 2 calls is 5/2 minutes. The average waiting time is 5/2. Okay. Another way to explain this is the following. Let me give that other method to obtain this. So if I want to have my waiting time in minutes, let's have x in minutes. So x is Poisson, not x, but let me write x tilde. Our x was calculating number of calls in 10 minutes, but let x tilde calculate number of calls in 1 minute. So number of calls in 1 minute will be, because we have 2 calls in 5 minutes, in 1 minute we have 2/5 calls. So Poisson with parameter 2/5. And because this is in 1 minute unit, then we will have waiting time is exponential with the same 2/5. Time unit is the same for both of them. So this is the number of calls in 1 minute. This is waiting time in 1 minute, in minutes. Okay, so we have created our models, Poisson 4 and exponential 2/5. Now we can easily calculate the rest, the probabilities. So probability that number of calls in 10 minutes will be less than 4. So x, not tilde, sorry, x, the number of events in a number of calls in 10 minutes was Poisson with parameter 4. And we are asked to calculate the probability that the number of calls, that is x, in 10 minutes, sorry, number of calls in 10 minutes, this is x, will be less than 4. So x is less than 4. So this is the sum of the probabilities that x is 0, so no calls at all in 10 minutes, plus probability that x is 1, plus probability that x is 2, and plus the probability that x is equal to 3. Let's recall what was the PMF for Poisson. So probability that x is 0, probability that x is k for Poisson was e to the minus lambda, in our case lambda is 4, times lambda to the k over k factorial. So x is 0 means I need to plug 0 here. I will have e to the minus lambda, so e to the minus 4, plus the probability that x is 1, e to the minus 4, lambda is 4, times 4 to the 1 over 1 factorial, plus I will not write the formulas for 2 and 3. So you can calculate this p part by using Poisson distribution with parameter 4. Now calculate the probability that we will wait less than 1 minute for the first call. First call and time between calls is modeled by that waiting time exponential, and that was not equal, but that was distributed as exponential with parameter 2/5. So the problem is asking to calculate the probability that waiting time for the first event, for the first call, will be less than 1 minute. This is in minutes, this is in minutes, so everything is okay. So this is exactly the value of our CDF at 1, and the value of CDF is 1 minus e to the minus lambda times t, lambda times this point. So lambda is 2/5 in this case, times 1. So 1 minus e to the minus 2/5. And the last part, calculate the probability that we will wait more than 3 minutes for the next call. So we are asked to calculate the following. Waiting time is larger than 3 in minutes. This is in minutes. So we can calculate 1 minus, well, let me use that formula for survival time. This is exactly e to the minus lambda 2/5 times 3. E to the minus 6/5. Now, another very important property of exponential distribution, it is the memoryless, forgetfulness, amnesia property. We have talked about that property for concerning geometric distribution. And this distribution, exponential distribution, is the only continuous distribution with memoryless property. So if we are talking about continuous memoryless distribution, it is exponential distribution. Let me give that property. So first, we have obtained this. So if x is exponential with parameter lambda, then the probability that x is larger than t is exactly e to the minus lambda t for any positive, non-negative t. Yeah. And this is the memoryless property. If x is exponential with parameter lambda, then the following property holds, and if this property holds for any t and s, then x is exponential lambda. So x is exponential lambda if and only if the conditional probability that x is larger than t plus s, given that x is larger than t, is probability that x is larger than this s. So we can cancel in some sense these t's, and I will give now interpretation for this. I'm not proving that, you can prove that easily. We have calculated that kind of conditional probabilities during one of our examples. So interpretation is the following. If x is the waiting time for something, for some event, then the probability that x is larger than s is interpreted as the probability that the waiting time will be more than s. Waiting time is more than s. Now, we can interpret this in the following way. This is the probability that waiting time will be more than t plus s, given that we have waited already t units of time. So this is waiting for another s units of time, another s minutes or hours or years, is independent how long you have already waited. So let me give an example. Say if you are calculating the waiting time, the time between two goals scored in a football game. So if you have waited, say, after one goal, if you have waited, say, 5 minutes, that doesn't increasing the probability that the next goal will be, say, in 10 minutes or more. So that is not changing that probability. Recall that the only discrete distribution sharing that memoryless property, this is the discrete version with m and n running from 0 to plus infinity, is the geometric distribution. And geometric distribution was waiting time for the Bernoulli process, Bernoulli events. So another interpretation, let me give another way of interpreting that and usage of memoryless property. We can use exponential distribution to model lifetime of some things. But we are using that lifetime modeling by exponential in the following case. That something, lifetime of something, I'm talking about that something needs to satisfy the following. It does not age, in the sense that the probability of functioning yet another time is independent on its current age. So our something, the lifetime of which, say, light bulb or something, or person, we are calculating the lifetime of person, need to be not wearing things, not wearing out gradually. It is just at some unpredictable time stopping functioning, say like memory chips. This shows that the lifetime of a person cannot be modeled by exponential distribution. It is not a good model because it is not satisfying this property. But say memory chip lifetime can be modeled by this. So we have noted that the only two distributions with memoryless property are exponential for the continuous case and geometric for the discrete case. Only these two are memoryless, share the memoryless property. And it is very interesting, a nice fact that it can be shown that the exponential random variable can be obtained as a limit of appropriately chosen geometric random variables. But I will not talk about that in our lecture. So this much about exponential distribution. Next time we will talk about normal distribution. So thanks, bye.